So we're going to talk about correlation and regression and really cover just enough so that we can move into doing SPSS analyses of data sets. So this will cover really the building blocks, and then we'll run through examples in SPSS. Okay, so what is a correlation? Well, it helps us understand the degree of association between two variables. And there's really two important properties. One is the magnitude of the relationship between the two variables, and the other is the direction of the relationship between two variables. Magnitude is expressed by the numeric value of the correlation. The direction is expressed by the sign, either positive or negative. So in a positive correlation, we might see the values of x increasing, and when compared to the values of y, a second variable, those values increase as well at the same time that the value of x increases. So what are examples of variables that could be positively correlated? Intelligence and annual income are probably positively correlated. We would expect people who are highly intelligent probably to have higher income than people who are less intelligent. It's not a perfect relationship. It may be a relationship that's slight. It could be 0.15, or it could be a stronger relationship, 0.85. But it's probably a positive relationship. Also, when we say positive correlation, keep in mind that if the values of x, say intelligence, decreases, and the values of y also increase, or decrease, I'm sorry, as x decreases, that's still a positive correlation because both variables are decreasing in value together. Now, a negative correlation is the flip, it's the inverse. In other words, as the values of x increase, the values of y decrease. So let's go back to intelligence. Let's assume that highly intelligent people are less likely to go to jail for any of a number of reasons. As we see IQ increase, we are likely to see number of instances of incarceration decrease. We would express that in a correlation with a negative sign, 0.15, if it's a moderate or small relationship, and a negative 0.85 if it's a very strong relationship. And if there's no relationship between two variables, the correlation is going to be 0. So a correlation can range in value from -1 to +1. And as we get closer and closer to 0 on either side, either positive or negative, we see less and less of a relationship between two variables. Now, what is regression? Regression is based on a correlation matrix. And what it does is give us more information than the degree of association between two variables. So when we do a regression, we actually create an equation that shows how much change in a predictor variable we should expect for every unit change in a dependent, or what we call a criterion variable. Now, it's also the case that once we know the scores on the predictor variables, we can then predict scores on a dependent variable with some error. So this may look a little frightening, but it's really fairly simple. That allows us to create a graph in which we plot x and y variable scores together, and it yields a number of interesting parameters in the equation. So y, the dependent variable that we are predicting, okay, sometimes called the criterion variable, is a function of, or equals, b sub 0, which is the y-intercept, that's where it connects to the axis, plus b sub 1, which is the slope of the relationship between x1, the first predictor variable, and the dependent variable, plus some degree of error. And error here is represented as how far the actual observations or data points fall off of the regression line. Okay, that's called error. It's also referred to as residual. And you can think of it as error in prediction. So the regression line represents a prediction of what we think will be the values of y, the dependent variable, once we know what the scores are on x, a predictor variable. And we'll create a regression line which represents the prediction. Now, obviously, this line can't account for all the data because the data will either be on the line, which is the unusual case, or somewhere off the line, okay? And that represents error. So this model right here represents a multivariate model, meaning there are multiple predictors of y. In other words, a set of x predictors that predict y. So in that case, we're going to modify this original equation such that y, the dependent variable, is a function of essentially the intercept plus the weights or slopes of every single predictor, and that the number of predictors is not provided here. It could be 1 or 2, it could be 20, and then plus an error term. Okay, and the error term simply represents the sum of all of these errors in prediction. The bigger this error term is, the weaker the relationship between the variables in the predictor set and our dependent variable. So we want to try to minimize error as much as possible. So we would like this term to be small in the equation because that represents a better set of predictors. Okay, let's go back to correlation. So I'm sure you've seen these in undergraduate statistics books, examples of a perfect positive correlation. If we were to draw a line through these data points, it might look something like that. A strong positive correlation might look similar to that, except what you notice is that the data points are falling off the line a little bit. So that represents anytime the farther these data points get off the line, the weaker the relationship, because there's more error again between the line, which is where we expect a value to be, and the actual observed data point. A weak positive relationship or correlation, there again you see these data points falling farther and farther off the line. Now, no correlation, what we see with no correlation is a line that gets flat. So you'll notice that the slopes are getting closer and closer to the horizon in terms of their slope. And when there's no correlation, you see absolutely no slope in the line at all. Why is that? Because knowing the value of x tells us nothing about the value of y. It doesn't predict y at all. Negative correlations have the opposite slope. So the slope starts going in a downward decreasing direction. And so that's what a weak negative correlation looks like, strong negative correlation, and then a perfect negative correlation in which all of the data points or observations align to the line. Now let's talk a little bit about what a correlation can't tell us much about. And first on the top of the list is curvilinear relationships. A correlation is an estimate of the degree of linear relationship between two variables. In other words, it's the estimate of how well x and y are linearly related to one another. So you can think of a linear relationship as a straight line. Can we describe that relationship in terms of a straight line on the graph that we plot? It's not a great measure of relationships that are curvilinear. So in this example right here, what you're seeing is a curvilinear relationship in which when we look at low values of x, they're associated with low values of y. So x is the horizontal axis, y is the vertical axis. So low values of x are associated with low values of y. But as we get to the mid-range of x, we get the highest values of y. And then as we get to the absolute highest levels of x, we get very low levels of y. Now, what kind of example would this be like? You can think of maybe test anxiety. So at very low levels of test anxiety, people may perform not so well or low on a test and get a lower score. You know, if you're not anxious about tests coming up, you don't study, and so that leads to a lower score. If you have moderate anxiety, it might stimulate a person to actually study for the test, and that's going to lead to higher scores. But if you have really high anxiety, it can be paralyzing, and a person may be so anxious that they just cannot perform on the test, so their scores go down. So that would be a curvilinear relationship. Now the problem is, if we were to draw a line through this data cloud that represents a linear relationship, first of all, we can't use the curved line, okay, because that's a non-linear relationship. So because a correlation is a measure of a linear relationship, we can only use straight lines. Well, the best fitting straight line in this example is a very flat line going through the data. Okay, and why is that a problem? That's a problem because a flat line suggests that there's no relationship between x and y. But clearly, there is a relationship between x and y. It's just not linear, it's curvilinear. So a correlation is not a good example or not a good statistic when there are curvilinear relationships involved. The other thing you should know, correlation does not equal causation. It can tell us the degree and direction of a relationship, but nothing really about the causal properties. We don't know whether x caused y caused x, or whether there was a third variable involved. And squaring r gives us r squared. Now you want to say, well, why do you want to square r? Well, an interesting property of squaring the correlation, which is notated by the symbol r, when we square r, what that does is it gives us the proportion of variance explained in one variable by another. Well, what do we mean by explained? All it really means is the proportion of variability in, say, x that is mirrored by variability in y. So as the proportion of variance explained increases, what we're observing are two increasingly related variables to one another. And the amount of variation that one variable explains in the other is increasing. Okay, so a high correlation leads to a high r squared. So if we get an r squared of 0.60, the way we would interpret that is that 60% of the variation in one variable is accounted for or mirrors variation in the other variable. That also means that 40% of the variation is not shared, it's not explained. And we can say that that's the percentage of variation that the two variables do not share in common. Now r squared ranges from 0 to 1.0, and you might say, okay, what does an r square of 1.0 mean? If you think about that for a second, what would an r square of 1.0 mean? Well, in order to get an r square of 1.0, the correlation itself, r, had to be 1.0. And what does that mean? That means that they are perfectly related to one another. The variables are perfectly related to one another. It's either a perfect positive correlation, positive 1.0, or a perfect negative correlation, negative 1.0. But they are effectively the same variable. In other words, when you have a correlation of 1.0 between two variables, neither one of them is measuring something that the other does not. so you're effectively measuring the same phenomenon twice using two variables. Okay, what's the effect of a restricted range on correlation? Now this is an interesting idea and concept, because correlations assume in the parameters of conducting the correlation that you're measuring the entire range of possible responses. If you only measure in a subset of the range of possible responses, you are engaging in sampling a restricted range on one or both variables. So here's an example of how that works. Imagine we have two variables, x and y, and we look at how they are related to one another by plotting x and y on a graph. And if I were to draw a line through this graph, I'd say, okay, that seems like it fits the best within the graph. And what do we mean by fitting the best within the graph? Well, I'm really trying to minimize the distance or the residual between these data points and the actual line. But you get a slope, and we would calculate a correlation from here. So you could get, this would come out and probably be somewhere in the 0.1 to 0.2 area, kind of a moderate, mild correlation. Now here's the thing with restricted range though. Imagine if I was only measuring a subset of values of x and a subset of values on y, and then drawing a conclusion about the relationship between x and y. What if I measured the entire range? So imagine that, rather than just measuring high cases that are in the moderate to high range on x and the moderate to high range on y, I measured the entire range of possible scores. What did that do to my line? Well, the new line we would draw has a different slope. Okay, so rather than having a weak positive correlation, we now have a moderate to strong positive correlation between the two variables. So a restricted range can have a dramatic effect on what we conclude about the relationship between two variables. The best example I can think of is GRE scores predicting first year grades in graduate school. The correlation there is not particularly high. Some of the research I've read is it's between 0.2 and zero point 0.3, and people say, well, why do you use the GRE if the correlation is only 0.2 to 0.3 in terms of GRE scores predicting first year grades? Well, if you think about it, there's two sources of restricted range there. One is that in graduate school, the grades are generally higher to begin with, so you get a lot more A's and B's and a lot fewer C's and D's than you do at the undergraduate level. So the criterion is actually restricted in its range to begin with. Also, think about who goes to graduate school. It's typically the folks who have the highest GRE scores, right? So you're not sending everybody to graduate school. Generally, just the folks who do well on the GRE are going to get in. So it's a subset of the range of possible scores there. Those two factors together will contribute to reduce the ranges for both variables and lead to a restricted range effect on the correlation between GRE scores and first year grades. You also can see an effect of extreme scores on a correlation. So imagine we have some data that looks like this, and we try to draw a line through there and figure out the correlation. Yeah, it might look kind of flat, not particularly exciting about that line. In other words, what we're saying is, hey, knowing the value of x tells us not a lot about the value on y, but then we throw in an outlier, right? And there goes that outlier, and look what happens to the line as a result. It changes and it shifts, and we end up with a stronger positive correlation. This is a bigger deal in small data sets. Usually in larger data sets, you throw an outlier in, it's not going to have a big effect, but in small data sets, one outlier can have a dramatic effect on correlations. The other issue maybe to think about is the relationship of third variables. And third variables fall under the general rubric of covariation. So imagine that we have a couple of variables that we're interested in. And we observe in a data set that, wherever there's a lot of churches, there are a lot of bars. Now, we don't know whether having a lot of bars causes churches to be present, or maybe more pessimistically, having a lot of churches causes people to drink. So we don't know the direction of causality, but we do know that wherever we see more churches, we see more bars. And you might think, well, that's sort of a strange relationship. Either the bars are causing people to go to church, or the churches are, it gets a little messy, right? Of course, there's a third variable involved, okay, that varies with both of these variables, and that is population. So wherever you have higher density population, we're going to see both more churches and more bars. So third variables could be positively related to our other two variables, and maybe perhaps completely account for the relationship between the two. So covariation is an important factor to consider whenever interpreting correlations. It's also one of the reasons why we look at regression as a way of understanding relationships between variables. Okay, so let's look at simple and multiple regression. Just go over some main points here. The main question that we ask in regression: does a predictor variable or set of predictor variables account for variation in a dependent, also called a criterion variable, above and beyond what we would expect by chance? In multiple regression, there is more than one predictor variable. So the predictor variables may covary to some degree. x1, which is the first predictor variable, and x2, the second predictor variable, may account for the same variability in y, in which case we would want to know that and understand the relationship between both of those predictors and our dependent variable. So as a result, if we've already entered one predictor in the equation, is it the case that the next predictor variable we will enter, x sub 2, predicts significant variability in y that was not accounted for by the first predictor variable, x sub 1. So, and that's really what regression helps us do, is it helps us partial out variance and assign it to individual predictor variables to understand their unique contribution and relationship to a dependent or criterion variable. So that's the multiple regression model, and again, here's the equation for the multivariate model and multiple regression. It is a linear additive combination of predictor variables that yields a predicted value, y, of the dependent variable. The predictor variables themselves may not be linear in terms of their distribution, but the relationship between them is linear, and it's represented by these plus signs. Okay, let's take a look at an example by Amy Gallo. This was in the Harvard Business Review in November 2015. And she was just giving an example of how regression worked. And I said, okay, imagine if you were interested in the relationship between sales in a store and monthly rainfall. So she said you take 3 years of data, going back 36 months, you get a whole bunch of data points, and plot out monthly rainfall against sales for that month. And the graph that she shows clearly shows what looks like a positive correlation, right? That as monthly rainfall increases, sales also goes up. And you might say, well, why would that be? Well, maybe it's the case that as rainfall goes up, people need to go to the store to get clothes, to prepare for winter, prepare for the wet, rainy season. They're more likely to buy the clothes that they need at that time. If we were to draw a regression line through the data, that's what we would end up with. So again, that looks like a very strong correlation. We draw the regression line, which is the best fitting line. I'm going to talk about in just a moment the criteria for determining the best fitting line, but this is what the regression line might look like. Now, this line will have certain properties. It will have an intercept with the y-axis. It will have a slope that represents the unit changes in x given unit changes in y. So if we were to write out that equation, in this case as an example, y equals 200 plus 5x plus the error term. Now the graph that we showed didn't have all those units on it, but the example that Gallo provides says, okay, this is what the regression looked like. We have a y-intercept here, and we have an error term of some size. If we were just to delete the error term off, we would say the simple regression equation would be y equals 200 plus 5x. Okay, so basically what it's saying is, okay, if you're going to predict y, you start by drawing your line at unit 200 on the y-axis, that's the y-intercept, and then for every incremental change in y, for every 1 unit change in y, we should increase the value of x 5 times. So if we look at the regression model, there's our y-intercept, that would be 200. There's our slope of the line, which is 5, which we see right here. And then we have to consider the error term, which is a slightly more complex notion here, and it helps us determine what the regression line is to begin with. That error term represents how far any observation deviates or falls from the regression line. We call this residual in regression. Okay, so it's referred to here as an error term, but for any observation, there is residual in prediction. In other words, we have the actual observation right here, and then there's some distance between the observation and the value that we predicted from the regression, because the regression is not of perfect predictive power. So there's the observation, and then there's distance, and we would measure this distance. And we do that for every single observation. So that residual error becomes important because it's going to help us decide what the regression should be. There are an infinite number of lines that could fit these particular data. So how do we decide what's the best fitting line? It all comes down to this residual error. So we would, across every single data point, calculate the distance of a data point from a proposed regression line. And then the criterion for the right line, the actual regression line that we will select, is the line that minimizes the distance on average from observed data points and their predicted location across all data points. So if I was to look at all these data observations right here, I would select the line, right, and its slope and how it gets all tweaked. It has to remain a straight line. But I would select a line that yields the smallest overall residual across all those data points. In other words, this green line, which represents deviation or residual, when I look across all data points, the sum of all these green lines would be the smallest amount. So what we're going to do that is first square the deviations or the residuals to avoid summing deviation scores to zero. You might remember doing that, by the way, when we were calculating analysis of variance. The smallest sum of squared deviation scores represents the best fitting regression line. There's even a name for this kind of approach. It's called the least squares regression. So when you hear least squares regression, what that means is the criterion for selecting the right regression line is the line that leads to the smallest value of sum of squared deviations or sum of squared residuals across all data points. That's a least squares regression. So, in a multiple regression, rather than regress one variable on the dependent variable, we are regressing a set of variables on the dependent variable. This is a little different than the example that we just looked at, in which we were just regressing one predictor variable on one dependent variable. In a multiple regression, we're actually looking at an entire set, and a big question then becomes whether the addition of a new predictor variable goes above and beyond our original or first variable in increasing the goodness of fit of the regression line. In other words, by adding in a second variable, do we account for a greater percentage of variation in the dependent variable y? Okay, so x sub 1, our first predictor variable, will account for a certain percentage or proportion of variation in y. We'll call that r squared. Now, is it the case that x sub 1 plus x sub 2 accounts for more variation in y? If so, if yes, then the variable is a statistically significant predictor of variance in the dependent variable, and that would generally be considered above and beyond what we would expect by chance prediction. So in a regression equation, we typically use the term capital R squared. The R squared, the R squared of the regression equation increases with the addition of the new predictor variable, and the increase is greater than what we would expect by chance or measurement error. When we get into SPSS, one of the neat things about it is it will tell us not only the amount of variation in y that's accounted for by the entire set of predictor variables, it will also tell us how much variation is accounted for by each individual variable. Okay, that's the basics of correlation and regression. You now have vast amount of knowledge now. you now know the basics. Those are the foundations, and you know enough so that when we go into SPSS, some of the data that we'll be looking at will make sense. So that'll be our next step to give it a go in SPSS.